Sure, yes.
You said this log normal is not a real random field. You're talking about this.
No, the fact that you have something has a Gaussian distribution doesn't mean it's a random field.
Okay. So why has it to be a random field in order to?
Oh, because the exclusion set formalism applies to Gaussian random field. It's derived for the Gaussian random field. So if the field is not random, then that it wouldn't work.
But you still have a Gaussian distribution.
But again, it has Gaussian PDF. Gaussian PDF is not necessarily so having Gaussian PDF is a necessary condition for being Gaussian random field, but it's not a sufficient condition. I can just take this. I'll just have a spherically symmetric object which has a Gaussian profile, right? It will have a Gaussian PDF.
Okay.
But it will be completely non-random, right?
Okay. So this is not random. Where can go wrong? What can go wrong?
Well, nothing of this applies if it's non-random.
Okay.
Right. So because you don't have any barrier. If the exclusion set formalism applies to a Gaussian random field, if you don't have a Gaussian random field, you cannot apply.
But which steps assume random in this derivation? Which step assume this random?
This assumes that your delta as a function of y is actually Gaussian is a random walk with a power spectrum. So it assumes that your steps in the exclusion set are not correlated, or at least they may be correlated due to the shape of the window function you choose. But at least for the sharp filter, you assume they're not correlated at all. I think the reason why it works is that in reality, the field is the ISM field is actually more random than you would think. But again, it's not. I don't understand why it works.
Okay. Thank you.
Okay.
Have your mic?
Yes. Okay, let's get going. So I can clearly see that bears are hungry today. The attrition rate is getting higher and higher. Okay, so the stereo feedback, right, the last piece in this course. So you of course understand that the stereo feedback is the biggest unsolved problem in modern galactic and cosmological and star formation studies. Right? So you will be the guys who will be solving this problem. And so to make sure I don't bias you too much, right? So this lecture will be very short. So let's first start with what actually stars produce, right? What actually escapes from stars. Stars affect the environments in many different ways. And you should probably all know that. So there is energy injection, which includes supernovae type 2 and 1a. There's energy in the stellar winds. There is momentum in terms of from supernovae, from wind, and then from radiation pressure. There's also mass loss, again from supernovae, from the wind, and from the normal stellar mass loss. So on average, if you take stars like the stars in the Milky Way, on average, our stellar population lost half of its mass over its lifetime. So, and of course, there are metals. And the metals are important because dust will form on metals and everything. So there's also dust, which is not directly injected by stars except by HGB stars, where it may form in the atmosphere. There's also cosmic rays, but the dust might actually form in things like supernova explosions. And the cosmic rays that form in supernova explosions as well. So there's dust and cosmic rays are not directly injected by stars, but they form in this process of ejection of something else. So the stars can affect the environment in a multitude of ways. And the first thing you should do is to basically look at those terms and say, okay, how much energy, for example, I get from those different components. Right? And when you do that, what you realize, and at least from cosmology's point of view, when we put supernova feedback is a minor correction to what the stars actually do. Right? This is the rate of specific luminosity. So it's ergs per second per solar mass. So it's a luminosity, it's amount of energy injected per second per unit mass. So those are as a function of time. This is actually supernovae. This is stellar winds, which in fact inject comparable amount of mass but do it early, amount of energy. But the light from stars, the bolometric luminosity from stars, is more than 2 orders of magnitude larger than that. So if you can harness the power of starlight, right, then you can forget about supernovae completely. They just become third order correction to the fifth order term or something like that. Right? So on the hands-on exercise that you won't be able to do, I actually let you plot some other components like UV light and ionizing luminosity, etc. on this plot. And it's also very useful, right? Just for understanding what stars do. So basically, the light of the light output of stars, not only bolometric, but even in different relatively narrow bands, just dwarfs anything else stars produce. So if you think about the feedback, it's not a supernova feedback, it's actually light feedback. Supernova is a small player, that's not how we're standing in second decimal place. So what do we know about the different components? So the stellar winds, their power scales as metallicity to some not very large power. So the lower the metallicity, the weaker the stellar winds become. And so if you want to study, say, early galaxy formation, high redshifts, maybe you don't have to worry about winds. Then radiation, as I said, radiation is a dominant energy production by stars. And the radiation pressure is something that we cosmologists have been talking recently in very excited terms. Right? So very hoping that it's basically the key to all answers. Turns out it's not, but let's talk about it a little bit. So if you have heavily obscured stars, then most of their light is going to be absorbed, right? Which means right away that you take all this energy and you actually absorb by the gas around it. So you can produce amount of feedback which is very large compared to the supernovae. So if you just take one photon, and of course one photon carries momentum, which is its energy over speed of light. So if you have a luminosity, the energy of photons per second, then the rate of momentum injection from this light into the medium around is L over C. However, energy is conserved. So if you now have dust that absorbs, stars are very obscure, it absorbs this light, the energy of the dust has to go up. And the dust will start radiating in the infrared. And if there is enough dust, if the optical depth in dust is actually high enough, that if the dust is optically thick to its own infrared radiation, then this infrared radiation will also do work on the gas around it. So it actually injects extra momentum. Right? Doing work is injecting extra momentum, just a second law of Newton. And so the total momentum injection from a star or a cluster of stars, you can in general case write it this way, where e to the minus tau uv is basically this term, because that also accounts for the fact that if stars are not heavily obscured, if tau is small, then this will become 0, right? And then there's no momentum injection for unobscured stars. And there's this extra term, tau IR, that can enhance, and it's essentially treat this as 1. If tau is large, this exponent is gone just 1. So this tau IR, if it's large, it increases the momentum injection and radiation pressure by the factor of itself. So if this factor is large, you can actually enhance the radiation pressure on top of what it already does. So this factor tau IR is easy to understand and something that comes up quite frequently, right? Where it's coming from. So if you think about a star which is being embedded into a cloud of very high density dusty gas, right? With how large optical depths in the infrared. Then what you have is the energy. As soon as photon leaves the star, it gets absorbed, right? And then energy propagates so for the outwards. So for this spherically symmetric cloud, the flux of energy at any radius r is L over 4 pi r squared, because energy is conserved, right? So when you integrate over the sphere, whatever leaves the cloud should be whatever is produced in the middle. So no matter, for the naked star, it's L over 4 pi r squared. But no matter how heavily embedded the star is, it's still L over 4 pi squared, because the energy has to be conserved, unless you put some wormholes inside to suck it in. So then the momentum, and so if you think about this radius, so the photons come here and live out there by scattering in the dust. So the momentum that you actually impart on this shell is just 4 pi r squared, the flux over c, then the opacity which you absorb times dr. Right? And that's actually, this becomes d tau. You plug the flux here, you get L over c times d tau. You integrate from the whole tau from the center to the outwards, and you get this tau IR term. So it's very easy to understand in this sense, algebraically. No, not algebra, you have to integrate as calculus. It's also easy to understand geometrically. Right? And it's usually considered in two different limits. So let's say we have one shell, very thin, but optically thick. So a very easy way to understand why the striping of infrared radiation produces more radiation pressure than what you have originally is consider photon as bouncing back and forth, right, inside this optically thick shell until at some point it escapes it, because it's a random process. You have optical depth tau, so you have a probability of escaping 1 over tau squared. So then it bounces back and forth, right? And so every time it bounces here, it pushes the shell this way, then it gets absorbed, irradiated, and irradiated photon goes here and pushes the shell that way. And by bouncing back and forth, you can clearly see that one photon, and by being irradiated continuously, it's not the same photon, right? It's being irradiated continuously, but it pushes the shell many, many times. And it pushes the shell actually tau times. What is harder to understand is a real case in which you have a continuum medium in which photon exerts a random walk until it leaves. Right? This is sort of an idealized case which never realized in reality. And in reality, you have some kind of cloud through which photons diffuse. Right? But in this case, it turns out that this case is also very easy to understand if you remember Shrek. Right? Ogres are like onions. Right? So the same actually applies to molecular clouds. So if I now take this molecular cloud, and I know that my photons diffuse from the center up to this point and then diffuse outwards. Well, I can take the inner shell out, because I really don't care what those photons did before they arrived. All I care that those photons came here and by being absorbed push the shell. So in that sense, this inner part actually is irrelevant, because I only care about photons that enter my shell. And for the same reason, the outer part is irrelevant, because as soon as I leave my shell, I really don't care what I do outwards. So in fact, in this case, it's no different from that case. If you imagine that this cloud is just made of concentric shells, narrow shells, which is delta tau. We have to sum of them over here and get a second case. So this is another example of actually a real Monte Carlo simulation showing you the stellar core and the cloud from which photon actually escapes. So it's a real path of one single photon. So this 2, 3, 4, 0, 4, 5 show you the places where optical depth is equal to 2, 3, 4, and 5. And the photon just scatters around. As it scatters around, it loses frequency, but it actually deposits momentum into the gas around it. And each scattering, sometimes it goes up, sometimes it goes down, but on average, because it's a random walk, you get this increase. Right? Notice that the number of scatterings is actually tau squared, not tau. Right? So you need to scatter 25 times to increase the momentum by a factor of 5. Okay, that's all fine, but how big is actually this tau R in reality? Right? So the first approximation for the tau R, you just take the absorption coefficient multiplied by surface density of your cloud, and you get some kind of average opacity through this cloud. So the opacity is actually kappa. Right? The opacity for infrared absorption and emission in dust it depends on temperature. So it's roughly scales like this from theoretical models. So the hot dust actually absorbs significantly more. Right? So what you need to do to increase this term, if you want to make radiation pressure stronger, the dust has to be hot enough. And then if you look at the observations, right, and try to estimate what this tau should be, right? So what you can do is to take, say, a cluster of stars. And for cluster of stars, you can compute, just take all the stars, say that's how much gas I had, compute the surface density, and then multiply it by this tau factor, and say, what is my tau IR in this cluster before all the gas was expelled? Turns out that for small ones, it's actually not a very big effect. For small ones, this tau IR is the order of unity, or maybe even less. But for big ones, it can really be important. So these big clusters begin their life in highly, highly embedded state. Right? And therefore, the feedback is enhanced by a factor of a large factor of 50 or even 100 by this infrared trapping. And so for them, it's those clusters for which radiation pressure will be a very, very strong effect, or dominant effect over everything else. So now we can put all this together, take all those effects and put them, say, in a spherical cloud. Right? You can argue whether it's a reasonable approximation or not, but at least you get a feeling about how different feedbacks affect each other. So what you have here is a bunch of lines. So the red lines show you the winds, and there are two sets of lines here. There's dashed and solid. So the solid lines are for solar metallicity, and dashed one for 10% solar metallicity. So the reds are wind, blue are supernovae, and black are radiation pressure for two different values of tau IR, 2.8 and 28. So this is just increased by a factor of 10, and this is what it would be for this particular setup. So as I said, radiation winds go down with metallicity. So if you have low metallicity gas, galaxies in the early universe, you kind of may not care about winds. And supernovae start somewhere around 5 million years. I think the first one goes at about 3, the first supernova for standard IMF. But the radiation pressure begins immediately. And as soon as stars switch on, you have radiation pressure. And in fact, even for modest value of this infrared trapping, your radiation pressure dominates over supernova energy injection. It's actually it's a momentum injection in this case, until times which are way too long compared to the age of the cluster. So for this cluster of stars, supernova irrelevant. It's the radiation pressure that disrupts the cloud. And in fact, we know that actually happens in reality, right? One of the most spectacular stuff forming regions in the local group is what? Huh? 30 Dorados. Previous correction, nothing compared to 30 Dorados. So 30 Dorados, right, this is known. It's entirely expanded by radiation pressure. Right? So the stars are still there, and the cloud is already disrupted. So the same you can do with energy. Of course, radiation pressure only contributes to momentum. The amount of energy contributed is actually very small. Right? So in terms of energy injection, supernovae do contribute, do dominate, relatively soon after the beginning of star formation event. But of course, what matters for the dynamics is both momentum and energy injection. In fact, momentum, in fact, is more important because energy can be cooled. Right? Momentum cannot be cooled. And momentum just pushes the gas and keeps doing it until you have momentum injection. So for actually destroying molecular clouds, right, the supernovae are totally irrelevant. Now we can say, well, okay, we have all those feedbacks, and just take and put them into in simulation and see what happens in the cosmological simulation. So when you do that, you find one result that's been around for 20 years. So this is, again, a cosmological. It's actually, it's a mini cosmological simulation. It's one cube. So it's one cell in a cosmological simulation, size of 40 parsecs. It's something that we can resolve today in modern cosmological simulation. It's not easy, but it can be done. So you take just one cell and put a stellar cluster at the center and see what happens with gas in this cell. And again, because it's 40 parsec, it's a large region of ISM, right? But it's our cell in cosmological simulation. So you do this, and then you switch different feedbacks and see how they work. Right? And so you put all the feedback together, what you find that the density in this one cube simulation goes down very rapidly. About 5 million years, essentially, the whole cell is evaporated. Right? And the gas gets heated to temperatures way above 10 million degrees. Now, if I switch off the energy feedback, I only count for momentum and say the energy goes stolen by aliens or something. Then I get this blue line. And you see the cloud lives for a little bit longer. Right? But nevertheless, and the temperature actually doesn't go up at all because it's only momentum. But nevertheless, the cloud is actually destroyed over 10 million years. So if you only have supernovae, right, so forget about radiation pressure and winds, if you only have supernovae and you include both momentum and energy, then you get this line, and I forgot what was the dashed one, sorry. So you get this line, and so you do destroy the cloud by supernova feedback, but it usually happens over time scale of 20 million years. So you're misestimating the lifetime for the cloud by ignoring all other feedbacks by a factor of 4 here. And then, of course, if you do what we'll all be doing for a long time, if you just put supernova energy, thermal energy into your gas, you get this red line, and then the cloud basically doesn't care that it has supernova explosions in it. And that's what's commonly called as overcooling problem. Right? If you only put the thermal energy as a feedback, then it all radiates away because you're putting it on very large scales. Right? 40 parsec is a large scale for ISM. Right? And we're now approaching 40 parsecs only now. A few years ago, we were talking about 100 and 200 parsec resolution simulations. If you put supernova energy in this large amount of gas, it just cools off and does nothing. Right? So this was a big problem for cosmological simulations for a long time. Right? So basically, all schemes which existed were tried to circumvent this overcooling problem. The fact that if you only put supernova thermal energy, then it cools away and doesn't do anything. So if you now go back and start thinking how I'm going to do it in my cosmological simulations, there is some kind of inconvenient duality between star formation and feedback. Remember, the star formation times, or at least on scales of hundreds of parsecs, is actually long. Right? Whereas molecular clouds are short-lived, and at lifetimes of 10 to 20 million years. So that's what often called as star formation is inefficient. Right? Oops, what happened? What happened? I'm not plugged in for whatever reason. Which is not good. Oh. Where?
Is it right now?
No. Well, then it will actually be even shorter.
Who can check it then?
That thing is not working.
And this one?
Wow, this one is not, is it on?
Yeah,
No.
but it's not working. It's dead.
Okay, this one is good. The other one too.
Okay, very good. Step. Don't break this thing. We are good if we can recover. No, we're not good. I was 1 second too late. It went to sleep. Sorry, guys. So you can think about the importance of feedback, for your life. What? Right. So let's keep talking. So the problem with star formation, right, that the star formation time scales are long. Right? We know star formation is inefficient in the sense that only a fraction of molecular gas goes into stars during the lifetime of one cloud. Whereas if the feedback comes from stars, that you naively would expect the feedback should be inefficient. Right? Star formation is inefficient, then feedback that comes from stars should be inefficient too. And so when you do this, when you put an inefficient feedback in your cosmological simulations, you get a Milky Way galaxy which has this rotation curve. Right? And anyone who ever saw a rotation curve of a Milky Way galaxy, which I actually showed in this class, then have immediate reaction. Right? So does it look good to you? It really sucks, right? So it has to be here, 200, right? So it's not just off, right? It's off by whatever factor of 3. So this galaxy is just totally screwed up. So the problem, so that's a problem, the generic problem for cosmological simulation. That star formation is inefficient, but feedback has to be very efficient. And how you combine those together is a open question, right? So this is just another example that not only my galaxies look really screwy, but other galaxies too look bad too. So for example, those are Max galaxies, a recent paper by Greg Stinson, and you see all of them have very big bulges, which means they all have very peaky rotation curves. Right? So this is a generic, the property that this rotation curve peaks very strongly in the center is a generic problem of cosmological simulations, and in fact, the higher the resolution, the worse the problem is. So for a long time, it wasn't noticed because the resolution wasn't high enough. But when we start getting resolutions below 100 parsec, then we start discovering this very peaky rotation curves. So again, this is a different set of simulations. They all have very large bulges, as you can see. So they all have peaky rotation curves. Now if we look at the real galaxy, they look disappointingly flat. Right? I sometimes call them dinner plates, but in fact, some of them are much flatter than dinner plates. Like dinner plates will be fat. But this is one of the galaxies. I forgot what the telephone number is. This has no bulge at all. So it's just a disk, right? A very thin one. It's probably width towards the length like 1 to 100. And this is not an exception. It's not like there's one special bulge-free galaxy in the whole universe. Most of galaxies, or not necessarily most, right, but at least half of galaxies like the Milky Way have no bulges. In fact, the Milky Way itself, as you know, probably doesn't have a bulge. It has a pseudo bulge. And I think that there's still debate is still going on whether it has a true bulge or not. But I suspect most people would claim that it doesn't. And so these bulgeless galaxies are very common. And if you go to masses slightly below the Milky Way, then there are many of them. So how you make a perfect disk without any bulge from a simulation point of view is a very difficult problem. So there's another problem, right? The fact that galaxies are inefficient star formers. So this is a plot that shows the halo mass, the mass of the dark matter halo. And this is the fraction of this mass which is turned into stars. So the way it's done observationally is by abundance matching, by matching the observed luminosity mass function or luminosity function of galaxies to the predicted mass function of dark matter halos. I'm not going to talk much about this. It's a very fashionable business nowadays, right? Abundance matching. There are good reasons why it's fashionable. It works pretty well. But what this one tells you is that you have the large range of dark matter halos from 10 to the 10, which really things are smaller than small and large Magellanic clouds, to 10 to the 15, which are basically as big as clusters that exist in this universe. Right? And they show you that these dwarf galaxies have a very small fraction of their mass in stars. So the galaxies which are most efficient star formers are around 10 to the 12 around the Milky Way. And so the Milky Way turned about 3% of its total mass, right, into stars, which again, this is unfortunately is not scaled by baryonic fraction. So 3% of total mass, you have to divide it by the baryonic fraction, which is 18%. So it will be about 17 or 20% of its baryonic mass turned into stars, but it's only 20%. Right? The universal baryonic fraction is somewhere between the floors or even higher. So, no, actually not. Right? Baryonic is here, between the letters. So this is the range that, this is the amount of gas that was not formed into stars. And even if you take an efficient star formation, even take this 2 billion years consumption time scale, the Milky Way is 13 billion years old. Right? So in 13 billion years old, you can take all its gas and turn it into stars, even if you do it on a 2 billion time scale. So the reason why it turned only 20% of its gas into stars, or 20% of its cosmic share of gas into stars, is probably due to feedback. But it's something that we need to understand. And as you can see, it's getting really bad, really small for very large halos and very small for very small halos. So the way I usually look at this plot, right, is that there must be two different feedback mechanisms to give you this. There must be one which suppresses things on this end, and this is probably stellar feedback. There must be another one which suppresses on that end, which may be AGN feedback. Right? I'm not going to talk about AGN feedback, but that's another important process that we're just beginning to think about. Right? So let's even think about this end. So what it means that feedback here is very efficient. It's efficient even by the most robust to feedback galaxies, right, like the Milky Way. But for these real dwarfs, it expels most of the gas. Right? So only a tiny fraction of the gas for these dwarfs, like the Magellanic Clouds, ever goes into stars. And the rest is, have to be expelled, otherwise it would be still in the disk and form stars. So the challenge really in understanding star formation feedback on galactic scale from cosmologist's point of view, right, is star formation is inefficient, but feedback must be very efficient. And so how you make efficient feedback from inefficient star formation is a trick, right, is a challenge. However, miracles do happen, right, even if you don't believe in them. So again, historically, there were many, many attempts to model feedback in cosmological galactic simulations with all kinds of models. Right? They're usually called subgrid models. Basically, you assume that you have a resolution element, a cell or a particle, whatever, 200, 100, now we talk about 50 parsec and 30 parsec resolution. And then you have to have some model that describes how stars form and how feedback operates. So historically, there were many attempts to put some models of star formation in feedback beyond just simple recipes. None of them was actually particularly successful. I'll just show if you, I'm not sure that was the first one. I don't know about an earlier one. I used one which was really complicated. See these expressions? It doesn't work too. Right, there are all kinds of even more complicated that use equations to describe different phases. There is something even with carrying around energy variables. So they all basically work or don't work to the extent that they do what these guys did. So kind of breakthrough in this field, again, I'm not sure I follow in history exactly, but I think the breakthrough really came from Gazolin team. And this is again the same plot. It's a stellar mass. Well, this is the plot I showed before, except that it's now multiplied by mass. It's stellar mass versus halo mass. What I showed you before was this divided by x-axis. So what I showed you before was just shifted by one slope down. And this green line is abundance matching result. It's observational result. And now all the circles are actually modeled galaxies. And they do lie on this line. So only a few years ago, modeled galaxies were like a factor of 10 off this plot. And so a couple of years ago, something happened. Right? There was a kind of breakthrough in understanding how, not an understanding, it was a breakthrough in modeling feedback in cosmological simulations. You also start getting galaxies that have, I would say, less peaky rotation curve. This is an Eris simulation. It's actually a different group, which are modeling the Milky Way, but they use the same trick to modeling feedback, which I'll explain in a second. So, and then they get the rotation curve for the Milky Way that kind of agrees with the data. It does have a peak still, but it's a much smaller peak. It's not 600 kilometers per second. In my Milky Way, it's only 240. And then how peak is the real rotation curve of the Milky Way is still a little bit an open question. And there also they actually visually start looking better. Can we shut down the lights? Can someone who can read French shut down the lights? Because there's one of those buttons that shuts down those lights, but I don't know which one, because I was pressing them at random and then things begin. Screen moved, No? You cannot do that? No, that's exactly what I did not want to do. Okay. Well, then we have to live with whatever this is. So again, this is now an image of this galaxy. And this is done by trying to model blue stars and old stars. And you see that young stars form a really thin disk. And there is a little bit of a bulge here because of this peak. So this galaxy is still not perfect, but it's not nearly as bad as it used to be. So what is this magic, right? And this magic, when they tell you what they do, right, is amazingly simple. Right? So all you have to do to make a realistic galaxy formation is to inject thermal energy from supernovae and not allow it to cool. So you inject thermal energy, but you just manually, in a code, switch off cooling in the place where energy is injected for something of the order of 10, or maybe 20, maybe 30, maybe even 50 million years. But you switch it for some modestly short period of time. So of course, it's a trick, right? You just do it in the simulation. Just take a physical process which should exist in reality and switch it off. Right? So it has no physical justification as such. And the fact that it works may be just a pure coincidence, right? But it also may be that something happens, something real physics happens on very small scales in such a way that on these large scales of the order of tens of parsecs and 100 parsecs, it appears as if cooling was switched off. Right? So not in reality cooling is switched off, but it is something else that mimics itself in such a way. And in fact, if you think that you may find what would do that, right? So actually, this is my quiz. So which of these 4 small-scale physical processes behaves as if cooling was switched on large scales? And for those in the back, I read it's radiation pressure. Right? So massive bright stars live for about 10 million years, and of course, radiation doesn't cool. So radiation pressure works like pressure which doesn't cool. You can have the thermal pressure of coronal gas if you allow the gas to expand to densities well below 1 particle per cc, and you somehow keep accumulating this, the cooling time in the coronal gas is about 10 million years. So it's not just delayed, it's just a long cooling time in very dense but very high pressure gas. So if you have a turbulent molecular cloud, the kinetic energy of the turbulent molecular clouds, they also decay on timescales of 10 million years, especially if they generated by feedback. Then finally, there's cosmic ray pressure. And cosmic rays, when they're injected from star-forming regions, they propagate through the galaxy. They do cool off. It's not a radiative cooling. It's a different way of cooling. They lose energy. And they lose energy on timescales of about 10 million years. So the quiz is, which one of those processes mimics the delayed cooling? Who is for A? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20. Who is for B? 1, 2, 3, 4, 5, 6. Who is for C? 1, 2, 3. Who is for D? 1. Well, that's an example of true democracy, right? Because every one of them is the right answer. Well, in a sense, maybe only one of them is the right answer, but we don't know what the right answer is, right? So every one of those possibilities is a plausible explanation why delayed cooling works in cosmological simulation, and which one of them, or no combination of them, is actually responsible. In reality, we don't know, right? That's why we don't know how to model the feedback. If we knew which one of them is the true answer, we would know how to model the feedback. Or it may be that it's not just one of them, it's a combination of several of those together. But as you can see, you can find many different, at least 4, and maybe if you think hard, you can find more, different physical processes that operate on small scales in such a way that on large scales, they behave as if cooling was switched off. So the fact that we now found a numerical prescription to tune our simulations to make good-looking galaxies doesn't mean that we figured out how to do the feedback. It's left for you to figure out which, if any of those, is responsible for operating as a feedback on large scales. Right, so if you now think about star formation model and feedback, it's a very short point I would like to make. Right? So the efficiency of the feedback, of course, does depend on how you model star formation. So we now have this canonical model in which star formation rate goes as the density to the 3/2 power. Right? So if you use this model in cosmological simulation, what you normally find that this rate, because it depends on density so steeply, converts gas into stars way too fast at early times. And so then, to make galaxies again look right, you have to add, in addition to this delayed cooling, you have to have sort of extra feedback on top of that at very early times to prevent galaxies from, prevent most of the gas going into stars very early on. So now if you say this, I call it modern because I like it, but just an alternative idea of the constant star formation time scale, and just like we've actually seen observations on large scales, in which case star formation rate goes linear with density, and because the time scale, the depletion time is 2 billion years, it means that essentially until redshift 3, you don't form that many stars in the galaxy, simply because the time scale is too long. So if that is the true model for star formation, that actually avoids completely this early feedback. But unfortunately, because it's only linear with density, it does not concentrate feedback enough. Right? This one is more concentrated because it's more concentrated towards the center where density is higher and where you need to destroy all those peaks and density spikes. This one avoids the problem of this early star formation, but then it doesn't concentrate the feedback enough. So from point of view of modeling galaxies today, right, actually neither of them is very good. Right? Unless you make some really bad assumptions like this early feedback, which is really strange. So what it really means is that at this point in cosmological simulations, the history of this field, we reached a point where all the models that we used kind of run out of steam. I think we are now identified them as not quite satisfactory. But how to modify them to make them more realistic is again is left for you to do. And then finally, this is my last 2 slides, right? Thinking about the future. So what really happening right now is that in cosmological simulations, we are approaching scales of tens of parsecs, which are now well inside simulation boxes of people like Ralph, people who study star formation. And so it's first time in history that there is an actually overlap in physical scales between cosmology and galaxy formation crowd and star formation crowd. And so again, it's the first time in history we can actually start talking to each other in a meaningful sense. So for example, we can talk to people like Ralph, right? And hope to use their simulations as our subgrid model. Remember, the best subgrid model is someone else's simulation. So it looks right now that there are many more details that we can account for, right? So there's not all gas makes stars equal, not all molecular gas makes stars equally well. So there's different feedback modes. If you consider the radiation pressure, supernova feedback, winds, right, they all do produce significant differences in details of modeled galaxies. So there is a hope here, in fact, is to try to use those models with very different forms of feedback to try to actually understand which one of the physical mechanisms operates. Right? So many of them operate like delayed cooling, but they operate as different sort of delayed cooling channels or whatever. So if I just look at galaxies that are modeled with different feedback mechanisms, this is the galaxy without the feedback. This one includes all the feedback. This is the same model I showed before for a single cell. Now you put all the cells together in a galaxy. This, for example, have very high optical depths in infrared. Right? The radiation pressure here is very strong. Here you have delayed cooling with 40 million years. And here you have a model which, in fact, treats turbulent energy as a separate hydrodynamic variable that you carry with you in the field. And in terms of general properties of the galaxy, if you look at density profile, etc., they all look similar, but you can clearly see differences in detail, right? This one has less hot gas, this one has more, how much the gas gets ejected, and the So this galactic fountain and the properties of the outflows are quite different. And so the hope is that by modeling galaxies with these different feedback prescriptions, you can figure out which one of them is really operates in reality. Right? And so on this optimistic note, I will finish. Right, that's left for you to do. So this. You want the bees or what? You want the bees? Huh? I think what we should do is the end of this course is to actually thank organizers, Yves, Pascal, and all other organizers, right, for organizing this school. And I hope that was useful for you. And so I expect in a time scale of your finishing your PhDs to know the answer about the feedback in galaxies and how it works and how stars form. Okay, so thank you, Yves, and thank you, Pascal.
I think Nick is. You will stay there up to tomorrow, right?
Yeah, well, I'll leave tomorrow.
So if you want to ask him some question, you will have some time. Or maybe you prefer to go cross-country skiing because the weather is so nice today.
Yeah, I might actually.
Or maybe you need to take time to prepare a new funny quiz. I don't know. Well, anyway, thanks a lot for these lectures.
Well, again, thank you for organizing this. Right? That's the lion's share of work is to actually organizing this.
A little typical Swiss gift.
That's what I was afraid of. You
don't
know
keep it in your pocket
what it means? It means I have to check my luggage now,
Right.
which I didn't plan to.
So I think it's now time to close this school. Thank you everybody for coming. I hope you enjoyed the week. I hope you enjoyed the place. And maybe see you another time. It's excellent. Bye.